The objective of this topic is to give you an overview of the gas metal arc welding process, equipment, and applications. Specifically, we'll look at the components in a typical gas metal arc welding system, the effects of wire feed speed and electrode stick-out on amperage, common shielding gases for carbon steel, the American Welding Society's classification for gas metal arc electrode wires, and the 3 types of metal transfer.
Gas metal arc welding is a versatile process used on everything from small parts to heavy fabrications. It can also be used for surfacing and build-up operations.
Gas metal arc welding uses the intense heat of an electric arc to melt a continuous electrode wire and base metal. The molten filler metal transfers across the arc to the work, where it fuses with the base metal to form the weld.
The gas metal arc process uses a power source to supply welding amperage and voltage for the welding arc. A wire feed unit, typically powered by a line from the power source, supplies the electrode wire to the weld. A gas hose carries shielding gas from gas bottles or from a gas manifold system to the wire feeder. A welding gun cable carries the weld current, shielding gas and electrode wire from the wire feeder to the welding gun. The gun trigger starts the flow of the shielding gas and electrode wire. It also closes the circuit that energizes the electrode. And a work cable and clamp complete the welding circuit.
Gas metal arc power sources include transformer rectifiers, generators, and inverters. They range in size from light-duty compact units to 100% duty cycle machines.
Duty cycle refers to the percentage of time during a 10-minute period that a power source can operate at rated output without overheating. So a 20% duty cycle means that a power source can operate for 2 minutes out of 10. And a 100% duty cycle means a power source can operate continuously at its rated output.
Most gas metal arc power sources are constant voltage machines. Constant voltage is important because it helps to maintain a consistent arc length.
As you can see on the volt-ampere curve, a very large change in amperage produces only a small change in voltage. However, the opposite occurs in a constant current power source like the kind used for shielded metal arc or gas tungsten arc welding. There's a very small current change for a large change in voltage.
The wire feeder delivers electrode wire through a liner in the gun cable assembly to the work. The wire feed speed control adjusts the amperage. The higher the feed rate, the higher the amperage. The lower the feed rate, the lower the amperage.
Drive rolls pull wire from the spool and feed it through the welding cable to the gun. Shielding gas is also supplied to the gun through the wire feeder.
The gun trigger starts the flow of shielding gas and wire. The nozzle directs the shielding gas to the weld puddle. And the contact tube, located inside the nozzle, applies power to the electrode wire when you press the gun trigger. This causes the arc to form between the work and the tip of the electrode.
There are a variety of guns for gas metal arc welding, ranging from small air-cooled units to large water-cooled guns for industrial use. Guns should be carefully matched to the amperage requirements and shielding gas for each application.
Shielding gas takes the place of the flux coating on shielded metal arc electrodes. It minimizes weld defects by preventing the molten puddle from reacting with oxygen and nitrogen in the atmosphere.
The most commonly used shielding gases for gas metal arc welding on carbon steel are carbon dioxide, or CO2, a mixture of argon and CO2, and a mixture of argon and oxygen. The selection of shielding gas depends on the application.
Electrode wire is specially alloyed to produce the best welds and comes in a variety of sizes. As you can see, the wire is much smaller in diameter than the electrodes used for shielded metal arc welding. There are several wire diameters available for gas metal arc welding. However, the most common are 35 thousandths and 45 thousandths of an inch.
The American Welding Society uses a series of letters and numbers, such as ER70S-6, to classify gas metal arc electrode wires. The E indicates that the filler metal is an electrical conductor or electrode. The R means the wire can be used as a filler rod for other types of welding. The two digits indicate the minimum tensile strength of the deposited weld in 1,000 pounds per square inch increments. In this case, the 70 means the weld will have a minimum tensile strength of 70,000 pounds per square inch. The S stands for a solid wire. And the last number, in the case of gas metal arc electrodes for mild steel, indicates a particular combination of carbon, manganese, and silicon. The typical percentages are listed in the manufacturer's data sheets.
Electrode extension, or stick-out, is the length of unmelted electrode extending beyond the contact tube. Maintaining the proper stick-out is critical to producing a quality weld because stick-out affects amperage.
By lengthening the stick-out, you decrease the amps slightly. And by shortening the stick-out, you increase the amps slightly. This gives you the opportunity to make fine adjustments to the amperage as you're welding.
Gas metal arc welding has several advantages over shielded metal arc welding. It has higher deposition rates, faster travel speeds. It's more efficient because you don't have to stop so often to change electrodes. Nearly all of the electrode is consumed, so there are no rod stubs to deal with. It's a cleaner process because it uses shielding gas instead of flux. There's less smoke and fumes with gas metal arc welding, and the process can be automated. There are some disadvantages too. GMAW is less portable, and breezes can blow the shielding gas away from the puddle, which makes it unsuitable for outdoor use without protection from the wind.
Gas metal arc welding encompasses three types of metal transfer: short circuit, globular, and spray. Each type of transfer depends on the combination of amperage and voltage, wire diameter, and type of shielding gas.
Short circuit transfer uses 100% carbon dioxide or a mixture of argon and CO2, along with the lowest range of welding currents and wire diameters. Because short circuit transfer occurs at lower amperage settings, it is most commonly used on thinner metals. Also, short circuit transfer produces a small, fast-freezing puddle, which makes it suitable for all positions: flat, horizontal, vertical, and overhead.
Globular transfer occurs at higher amperage and voltage ranges than short circuit transfer. In globular transfer, the molten filler metal forms a ball up to twice the diameter of the electrode. The force of gravity eventually causes the molten ball to transfer to the puddle. Globular transfer is not commonly used because it produces large amounts of spatter, and its dependence on gravity makes it unsuitable for out-of-position welding.
Spray transfer occurs at higher amperage and voltage settings with larger diameter wire in an argon-rich gas shield. Because of the intense heat generated by the process, spray transfer may not be suitable for some thinner metals, and spray transfer is limited to the flat and horizontal positions because the puddle is so fluid.
There's a variation of spray transfer called pulsed spray transfer. In pulsed spray transfer, the power source pulses the amperage up to several hundred times per second between a low background power level and a high current level. At the high current level, a small droplet of filler metal forms and transfers across the arc to the puddle. Spray transfer using pulsed power operates at lower average current levels than conventional spray transfer, which makes it more suitable for all-position welding.
Gas metal arc welding is one of the most popular welding processes because it's suitable for ferrous and non-ferrous metals, ranging from thin to unlimited thickness. It's also one of the most versatile processes because it can be applied semi-automatically, where the welder provides the travel and guidance along the joint, mechanically, where a machine provides the travel and guidance and the operator does the setup and monitoring, and automatically, where all aspects of the process are controlled by the equipment.